going to go through one of the videos, or part of the video from PM Robitaille, otherwise known as the Sky Scholar. Well, he calls himself the Sky Scholar, but he actually doesn't know much about astronomy. He knows a lot about chemistry, but it's one of those things. Somebody out of their own expertise. He's one of these people who he's actually a trained scientist, but he doesn't like relativity, and that's where a lot of these cranks or alternate scientists or whatever you want to call them come from, is that they don't like relativity for one reason or another. Sometimes it's religious because they don't like the idea of the Big Bang. Sometimes it's just they just don't like the concepts like black holes or the Big Bang or ultra dense stars. And I don't know why Robitaille doesn't, but that's one thing he doesn't like. And he does this whole series. He's just done this whole series on white dwarfs, so I'm going to go through it. Okay, now it's his turn.
Point of view of a chemist, let us outline the properties of an ideal gas. Such gases are characterized by 5 properties, which can be summarized as follows. First, the atoms within an ideal gas act as point sources or particles with negligible volume compared to the total volume of the gas. Second, all collisions which occur between the particles in an ideal gas are elastic. That means that the particles are not deformed as a consequence of the collision, and that no net kinetic energy is lost during the process. Third, there are no net forces between the particles, whether they be attractive or repulsive. Fourth, the particles move randomly in accordance with Newton's laws of motion. Fifth, the volume is defined by the container and pressure is generated at the walls, wherein all collisions are elastic as dictated by kinetic theory. Now let's start with the last point, namely that a container must be present in order to properly characterize the pressure and volume of an ideal gas. Of course, the temperature of the gas is related to the average kinetic energy of the motion of the particles. In setting up their...
The thing is gravity can keep particles in the gravitational field, and as he says, it's dependent on depends on the mass of the particles and the temperature of the particles. The higher the temperature, the more energy they will have, and therefore they'll be able to, if they're light enough, will be able to escape. But he will point out, later on he'll show how the Earth will bounce particles, and the bounce off the Earth will lose energy and keep the particles in. But this also goes for the sun, because the sun, the particles will fall down will hit particles below it and lose energy as they collide with one another. It's not an ideal gas, really an ideal gas. Plus, also in nebula, there is a lot of what astronomers call dust. Dust is silicon covered with ice, which also have chemical compounds on it, and spectrographic evidence like this is the Pillars of Creation, the Eagle Nebula. This was first taken by Hubble. I think this is the James Webb version. But it has stuff like glycine and alcohol. There's actually tons of alcohol in space. I'm amazed Budweiser hasn't been into space. But there's all these trace molecules, and what happens is these particles will hit one another and they'll melt just a little bit of ice on the surface, and they'll start sticking together, and they will create mass. What starts this can vary. There's stellar winds that flow through nebula. There's also things like supernova, which will push stuff together. In the early universe, before there was all these particles, the expanding gas from the Big Bang combined, and like the black holes in the center of galaxies were formed, and the earliest stars, and that made the heavier elements.
Dealing with gases. Ordinary gases like helium and even molecular hydrogen at ordinary pressures and temperatures are elastic. Now, what am I saying exactly? Just consider two helium atoms initially far apart from one another. Since they are only two atoms, we can ignore temperature completely and start with our two atoms at rest to simplify the analysis. Because the astronomers assume the collapse of an ideal gas, we can consider that the helium atoms are acting essentially like rigid billiard balls and that their collisions are fully elastic. That is to say that, during an elastic process, any shape distortion during the collision is immediately and perfectly reversed. Further, let us, like the astronomers, consider the gravitational attraction between the two atoms. What will happen? Well, because the atoms are experiencing weak gravitational attraction to one another, they will eventually start to move.
That's not actually what astronomers think forms, how stars start to form. It could be a number of things. It could be a nearby supernova or a solar wind or any number of things. Like the above picture, the picture you're seeing here is from the Orion Nebula, which has four giant stars in the center, which have huge stellar winds that may push gas across to each other. Gas clouds can collide on their own in space. The spiral arms in galaxies are where these some of these gas clouds can combine and may trigger star forming situations. Magnetic fields may take effect. As I said, these clouds also have small grains of dust, which is ice coating silicon or metal, and they may stick together and start clumping together and start forming stars or seeds of the stars and planets in the area. So it's not atoms just colliding together. It's things forcing the atoms to be within a certain density and pressure to overcome the kinetic energy of the particles hitting one another. So it's not just one thing. This is a very oversimplified process, and I think it's made that way to make his point.
Move towards each other, accelerate, and eventually collide. Immediately after the collision, the velocity of each particle will be the reverse of the incoming velocity. With time, the particles will slowly come to rest once again. The process will be repeated over and over again if the system has no losses. As a result, gravitational collapse will never occur. The system is always just converting potential energy to kinetic energy and vice versa. We will set up a harmonic oscillator without losses and no collapse. This is a key point. In order to have gravitational collapse, the collisions within a gas must be inelastic. One must have the ability to permanently distort the billiard balls, for instance, in order to lose kinetic energy as heat. In that case, collapse would occur, but this would never happen in an ideal gas. Next, let us consider that many atoms are involved. Let's say several thousand, in order to make Boltzmann happy, because it takes many particles to speak of macroscopic thermodynamics. In any case, the problem for the astronomers would be that the system adopts a temperature related to the average velocity of the particles. Now, in kinetic theory, gravitational forces play no part. Why is that? The simplest answer comes from our first example with only two atoms. When dealing with an ideal gas, all collisions are considered elastic. There is no way for the system to lose energy. Therefore, there is no net effect of gravity on the position of the particles. Everything is described by kinetic theory without invoking gravity. That is why gravity is never considered in an ideal gas. In this second example, we now have many atoms in motion due to temperature. Unlike the first example, this is a thermodynamic system, and the laws of thermodynamics will come into play. As a result, the entropy of the system must increase with time in order to adhere to the second law. In reality, the system must expand over time. This acts to increase entropy as required for spontaneous processes. All the collisions are elastic and there is no way to lose energy. This is why gravitational collapse cannot occur in an ideal gas. The fact that collisions in an ideal gas are elastic acts to completely eliminate any net effect of gravity, and the gaseous cloud continues to expand. In reality, that is actually what has been observed in astronomy, as one can gather in this paper. Most large molecular clouds have been shown not to be gravitationally bound, yet a few are gravitationally bound. So how does one explain these cases? The astronomers tried to account for this by invoking localized changes in density within the cloud, for instance. But again, if everything is in gaseous state, then collapse should not.
As you see in the image, there are several large bright areas. These are probably stars being formed by gravitational collapse. And the rest of the cloud may be dissipating, but there does seem to be some local star formation in this cloud.
For the sake of simplicity, we will ignore the sun, the presence of solar winds, and the magnetic field of the Earth. As we know, the lack of a magnetic field allows a solar wind to strip the planet of its atmosphere, and we will not be concerned with this problem. Let us further assume that all gas atoms in the Earth's atmosphere behave like ideal gases. Now, these gas atoms get to strike one another as a result of elevated density and the kinetic energy of motion of the gas, which is associated with the temperature of the Earth's atmosphere. Since everything is said to act as an ideal gas, those collisions will always be elastic. We can also ignore the gravitational attraction between the gas atoms, as we noted above, since this has no net effect relative to collapse in an ideal gas. At the same time, the surface of the Earth is present, and the Earth is applying gravitational attraction on the gas atoms. This acts to pull the atoms of the atmosphere towards the Earth. Some of these atoms get to strike the surface of the Earth, and these collisions, in this case, are not elastic, even if the gas molecules themselves were acting as essentially rigid billiard balls. Some of the kinetic energy of the gas particles gets to be transferred to the Earth as heat in an inelastic process. This occurs because the surface of the Earth is not perfectly rigid. As a result, unlike the two-atom case above, in this instance, the gas particles have less velocity when their direction is reversed as they move away from the Earth's surface because kinetic energy has been lost as heat. In the end, this helps to ensure that the gas atoms above the Earth become gravitationally bound. Once again, this is because the collisions with the surface of the Earth were inelastic. In this case, the spatial extent of the atmosphere did not need to increase to satisfy the second law. Energy was being dissipated into the surface of the Earth, and that is where the entropy change is occurring. At the same time, some atoms will still manage to escape the Earth's gravitational attraction. For example, that is the reason why our planetary system is always losing helium. The helium atoms are slowly escaping the Earth's gravitational field. In reality, a second effect also comes into play here. The sun can heat the surface of the Earth, and a gas atom striking the Earth can actually gain kinetic energy as a result. This creates a steady state wherein the atmosphere maintains a certain density distribution with elevation. If the sun was not present, then the atmosphere of the Earth would simply collapse onto its surface over time as the entire system cooled. This analysis helps us to understand why some molecular clouds do not appear to expand. It is purely a manifestation that condensed matter is present in these clouds. That is what creates local inhomogeneities due to the presence of inelastic collisions.